let's get to the subject matter of today, which is parallel lines, and it's more or less related to what I just discussed. So what are parallel lines? Well, for this, we have to go all the way to the days of the Greeks. Okay? And we find Mr. Euclid, who more or less synthesized what the Greeks believed and what the Romans later on passed on to us, to the Western world, about what geometric figures were, specifically for the subject matter today, the parallel lines. Okay, what is a parallel line? Or parallel line, what are they? And you find it in definition 23, book 1, he says parallel straight lines are straight lines which, being in the same plane and being produced indefinitely in both directions, do not meet one another in either direction. So how can a line grow? I mean, if he's going to extend the line, where does the line begin? Where does the line end? What is he talking about? Well, again, we had that problem the other day where, all these little dots that you see there, those make up the line. A line is made of points. And it turns out the points are zero dimensional according to Mr. Euclid. They have no, what he said, which has no part, meaning it has no dimensions. Okay? And so if it has no dimensions, he's just described nothing. So what is he talking about? Well, he's talking about locations. Let's say it bluntly. That's what he's talking about. And if a line is made of locations, of all these points, of all these, he calls them points, these dots, but they're not dots. The dot represents a location. And what we're talking about is an itinerary. He's talking about, a series of locations. That's what we call an itinerary, a trajectory, perhaps an orbit if it's circular, Okay, so that's Mr. Euclid's version. Hopefully we improved on it after all these years, right? But I want to just make a comment here. Someone who, made a comment in the primary analysis of Euclid. It's by Clark University. You can look it up. And he says, Euclid develops the theory of parallel lines in propositions. There was another, I think it's I-27 through I-31. Anyways, I covered those. And if you look at those, none of those are theories. Now, this is a guy from today. This is a guy who's alive today. He's a professor at Clark University. He wrote this. He says, the theory of parallel lines. These are not theories. These are descriptions, definitions, maybe tautologies. None of these are theories. So let's start there. These people don't have any idea what a theory is. A theory is an explanation. The word theory and explanation are synonyms. Perfect synonyms. There is no other definition of the word theory valid in science. Okay, so a theory is an explanation. Explanation is a theory. And none of these propositions that Euclid had are theories. Okay, so you can look them up, read them. You'll find out they're all either descriptions, definitions, or tautologies. None of them are theories. So I don't know why he introduced the word theory. It just shows his ignorance. And this is a professor at Clark University. Okay, what's the modern version of our parallel lines? Hopefully we improved on Euclid. I mean, after 3,000 years, you would think that, hey, we're beyond Euclid. Okay, let's find out. And this is the definition we have today out there. It says parallel lines are lines in a plane which do not meet. That is, two straight lines in a plane that do not intersect at any point are said to be parallel. That's in Wikipedia, and you'll find it everywhere. It's not only in the Wikipedia, okay? Okay, there I do two lines. It's in a plane. The plane is a specific plane. It's called a square, okay, in science. And we have the square. We have two lines drawn there on this plane, and they do not intersect. So are they parallel? Do you think those two lines are parallel to each other? Because it meets the definition. It says lines that are in the plane which do not meet. These two lines do not meet, do not even touch each other. So that definition has a problem. Okay, because it says two lines. There we have two lines, and they don't meet. And you say, Bill, but you cheated. See, those are not lines. What do you mean they're not lines? No, those are line segments. Line is something else. Oh, okay. So what is a line? Okay, first let's find out what a line segment is so we can contrast it. Here's the notion of a line segment. Okay, line segment is a part of a line that is bounded by two distinct endpoints. Okay, there you see the two endpoints are red, colored them red so that you can know what an endpoint is, and contains every point on the line that is between its endpoints. Okay, so that's the so-called line segment. What they're trying to tell you is that this line segment has a beginning and an end. Okay, and it's finite. Okay, a closed line segment includes both endpoints. An open line segment excludes both endpoints, and a half-open line segment includes exactly one of the endpoints. Okay, fine. These are categories. Okay, so they're saying that the two on the left that I drew there, they're not lines, they're line segments, and they're talking about lines. Okay, my error, my mistake. Okay, so here we see that if we follow their definition of line, you have to extend these lines, and once you extend them, okay, they do cross, but you know, they're outside, in this case, they're outside the square, which is a plane, and what they're saying is the plane is infinite, whatever that means. I never saw an infinite figure, so you know, they're just saying it's a continuous surface, so to speak. So it extends forever, and so you can extend the lines forever as well. They're not talking about a specific plane like a circle or a triangle or a plane or a square, because if you did that, you would have to remain within the boundaries of that square, of that circle, and so on, and maybe the lines don't intersect. But again, they're saying those aren't lines, those are line segments, and the plane is infinite. In other words, it's not a figure. They're not talking plane, they're saying it's just a continuous surface that extends forever. That's what they're saying. Okay, so let's work with those definitions. But for this, we have to go back and find out, you know, what a line is. And we look up the definition of the word line, and we're horrified. Okay, why? Because we find out that it's a primitive concept. Whoa, primitive concept. Okay, let's see what it is. All definition, this I think is out of the Wikipedia also, but all these places have the same notions. All definitions are ultimately circular in nature. So they start already with a warning. Don't expect the definition of the word line, because all definitions are circular. Okay? Since they depend on concepts which must themselves have definitions, a dependence which cannot be continued indefinitely without returning to the starting point. Yeah, it looks like these primitives are going around in circles, you know? Okay? To avoid this vicious circle, certain concepts must be taken as primitive concepts, terms which are given no definition. Sounds like you're eluding the definition because you can't define. Because as long as you define in terms of other words that do not need specific definitions, as long as you can distinguish, then you have a valid definition. To say that you can't define any term in the dictionary, especially those that we use in science, you know, that the one that make or break your case, your theory, that's just eluding the question. You have to make clear to the audience what you're referring to when when you're going to use the word line. And if it's a geometric figure, you're not going to define it, because you don't define figures, you point to them. And of course, you can't point to a one-dimensional line, especially if it's an itinerary, a bunch of locations, which is not a geometric figure. And so on and so on. So that's why it's so circular. And these poor primitive mathematicians are just going around in circles. In geometry, it is frequently the case that the concept of line is taken as a, what? Primitive. Okay, so these people are eluding the question. That's all they're doing. And just in case, you know, they have also the back and forth line. Okay, this is the back and forth line. The concept of a primitive notion may be too abstract to be dealt with. In this circumstance, it is possible to provide a description or mental image of a primitive notion. Yeah, because all you have to do is point to it. That's why you have a mental image. You don't. That's how you present a figure in science, especially in physics. These are not true definitions and could not be used in formal proofs of statements. The definition of line in Euclid's Elements falls into this category. There is no generally accepted agreement among authors as to what an informal description of a line should be when the subject is not being treated formally. Okay, so yeah, these people are, all they're doing is going around in circles and back and forth, you know, eluding the question. And the question is, what the hell is a line? And they say, well, we can't define it. Well, not only you can't define it, you can't point to it because it's one-dimensional. You can't draw it because whatever you draw is two-dimensional. And then you extend it forever because you're talking about an itinerary, a bunch of locations. So what the hell are you referring to? What is this famous line of yours? And if you don't know what a line is, much less can you know what two parallel lines are. Or maybe we can. Let's find out. Maybe we can. So here we have, what is a line? Well, it's a bunch of points, remember? And what is a point? A point is a primitive notion also. We have all these cavemen, all these Neanderthals, you know, and it's all primitive. That models an exact location. So what is a point? It's a location in space, they say. It has no length, width, or thickness. Okay, so what are we talking about? We're talking about location. And a line is a set of all points. In fact, you'll find another statement there that says, when n equal 1, the set of all such locations, okay, that's what they're talking about, is called a one-dimensional space. Okay, so what are they talking about? They're saying that a line is a bunch of locations. An example of a one-dimensional space is the number, what? Line. So they're talking about numbers. What are those numbers? They're locations. They designate or stand in lieu of locations. So we were talking about locations, locations, location. If you want to sell your house, just use that term, okay? Okay, so what is a line? Well, here it is. Okay, here's illustrated. I illustrated this the other day. It's a bunch of locations. It's the locations the turtle had in each frame of the film, of the Universal movie. That's what it is, just a bunch of locations. It's an itinerary. It's the itinerary of the turtle. That's what a line is. They're not talking about a geometric figure. They're talking about trajectories, okay? And so what does this take us to? Well, here's what two parallel lines are, okay? This is essentially, what it is a, what they've defined is a way to come up with parallel lines, okay? They're saying, if you want to know if these two lines are parallel, hey, all you have to do is go to infinity. Okay? How to find out whether two lines are parallel? That's what they're trying to tell you or describe or whatever. It's a specification of how to tell whether two lines are parallel or not. And they say, line is a series of locations. That's what it is. You add all these locations until you get tired and beyond. You just can continue putting dots, locations, one right after another, all the way to infinity, and hopefully you come back someday, okay? And ensure a location of one itinerary does not cross the path of the other. Until you verify that, you can't come back. So you have to follow these lines all the way to infinity, right? Wherever infinity is. And only if they cross can you come back and say, they did cross, so they're not parallel. And meanwhile, you have to continue rolling because, that line continues growing on you. It's a bunch of location, a bunch of itinerary. You got to continue going straight, known as rectilinear trajectory. So you have to go on and on and on and find out if anywhere do they cross. Until they do, you can't come back. Okay, so here's what we call parallel lines. Very simple. It's very objective. You just stare in 1 second. Without any wording, you essentially understand what parallel lines are. Okay, here it is. Okay, these are parallel lines. They're known as parallel lines. What's the criteria? Equidistance. Okay, they maintain the same distance throughout. And are they eternal lines, a bunch of locations, itineraries? No. What they are is what these people call line segments. It's not even that because the line segments are also made of points, which are locations. These are not a bunch of locations. It's a stick. That's what it is. A continuous stick made of a single piece. And they just maintain the same distance from where you see it begin to where you see it end. That's it. And those are known as parallel lines. See how easy it was all these years? All you got to do is point and say that's a parallel line. Why? Because they're equidistant. And we're done. Even a child understands that. You don't need to extend the line and say it's a bunch of points, it's an itinerary, it's an orbit. We don't need any of that. Okay? Understanding parallel lines is one of the simplest concepts in science. I don't know about geometry, but it is in science.